Alright, welcome back to the AI Research Roundup. I am your host, Alex. Today we're looking at a paper that's been getting a lot of attention. It's called KVzip, Query-Agnostic KV Cache Compression with Context Reconstruction. So when LLMs process long documents, they store the context in something called a key value cache, or KV cache. This key value cache is essentially the model's short-term memory. The problem is, this memory gets huge with long contexts, which uses a lot of resources and increases latency. KVzip introduces a clever way to shrink it with almost no performance loss. And for those of you who want to try this out yourselves, the authors have actually made all their code public. They've put together a GitHub repository for KVzip. It has everything you'd need to get started. Things like a quick start guide, demo and evaluation scripts, and even instructions on how to apply the technique to new models. It's a really great resource if you want to see this compression method in action. Okay, so this first figure really clarifies the core problem KVzip solves. It compares different strategies for what's called key value eviction, which is basically deciding what information to keep in the model's memory. With older methods, like query-aware eviction, the model has to reprocess the entire document for every single new question. This involves a slow step called the prefill, and repeating it is very inefficient. Another idea is to reuse the memory from the first query, but that hurts performance on later queries. KVzip's approach is different. It creates one general-purpose compressed memory up front, which works great for many different questions without any slowdowns. So this figure gives us a great overview of how KVzip actually works its magic. After that initial prefill creates the full key value cache, the model is fed the original context again, but this time with a special repeat prompt. The goal here is to make the model reconstruct the original text. As it does this, it measures something called cross-attention, which is basically how much the model focuses on each piece of the original context in order to rebuild it. This process generates an important score for every key value pair, and the least important ones are simply dropped, creating that much smaller compressed cache for future queries. Alright, and this next figure reinforces that same idea by framing the process in a slightly different way. It views the LLM as a context encoder-decoder. So the encoder part is that initial prefill, where the model reads the context and encodes it into that full key value cache. Then, after the eviction step where unimportant pairs are dropped, the model acts as a decoder. It uses a prompt like, repeat the previous context, to try and reconstruct the original text using only the smaller compressed cache. This is the core test of the compression's quality. Alright, so after that whole reconstruction process, how well does the resulting compressed cache actually perform? Well, this chart gives us the answer. We're looking at accuracy on the squad benchmark, using a Llama 3.18b model. The x-axis shows the key value cache budget ratio, which is just the percentage of the original memory that we keep. What's really striking is how KVzip in red hugs that top green line. Even when we throw away 70% of the cache, at a 0.3 budget ratio, the accuracy barely budges. Meanwhile, reusing a cache from a previous query, shown in blue, just plummets. Okay, so that last chart showed that KVzip's performance stays strong, while reusing a cache from just one specific query fails badly. These next heat maps really dig into why that is. They compare the importance scores of key value pairs across different kinds of tasks. The first three plots pit KVzip's repeat method against question answering, summarization, and reasoning. You can see a strong correlation in the bright colors, which means the information important for simply reconstructing the text is also important for these other, more complex tasks. This is the key to its general-purpose success. And this next chart provides a really clear visual reason for why KVzip works so well. It's a histogram comparing the importance scores from the initial prefill stage, in blue, with those from the reconstruction stage, in red. What's immediately obvious is how the red distribution is heavily skewed to the left, with a massive spike at the very low end of the score range. This indicates that during reconstruction, the model considers most of the key value pairs to be unimportant. This sparsity is the key. It's what allows the model to confidently throw away so much information. Okay, so we've seen that this reconstruction process is great at finding what's truly important. But there's a practical catch. For a really long document, calculating those attention scores across the entire thing at once would be a massive computational headache. This figure shows the clever solution, which is called chunked scoring. Instead of looking at the whole context at once, KVzip breaks it down into smaller, manageable chunks. It then calculates importance scores for each chunk individually, which keeps the memory and compute costs from exploding, making the whole method practical for extremely long documents. To wrap things up, KVzip offers a really elegant solution to the key value cache problem. By using a simple reconstruction task and cleverly breaking it into chunks, it can figure out what information is truly essential before it even sees the final query. This is a huge step forward for running large language models on extremely long documents, making them much more efficient. Thanks for tuning in to this AI Research Roundup. I'm your host, Alex, and I'll see you next time.